Okay, my name is Wolf McNally. I'm lead researcher for Blockchain Commons. Blockchain Commons is a community that brings together stakeholders to collaboratively build open and interoperable, secure, and compassionate infrastructure. We design decentralized solutions where everyone wins, and we're a neutral, not-for-profit that enables people to control their own digital destiny. So in this talk, I'm going to introduce you to extensible identifiers, or as we call them, XIDs. And this is, we're used to having various kinds of identifiers on the internet, our email addresses, and our computers have identifiers, which are our IP addresses. And but there's a need for identifiers that are much more secure, much more privacy respecting, and so on. And so building on the stack of technologies that um, that Blockchain Commons has been developing for several years now, we're introducing this form of identifier, which is still in its very early stages, and we're very interested in the community's feedback. So XIDs are a decentralized identifier. Decentralized basically meaning you don't need a central authority to create it or maintain it, hold it, authorize it. You can create it entirely on your own, and other people, and then you can distribute it to whoever it makes sense to. We're using Gordian Envelope, which we've talked about in a number of our other talks, to go beyond the capabilities of W3C distributed identity identifiers, DID controller documents, and W3C verifiable credentials. So you're going to be seeing, if you're familiar with those things, you're going to be seeing something that goes well beyond those capabilities. This is still early research. We have a document up at HackMD, and there's a QR code. We'll also put this URL in the video if you're watching this on YouTube or any of the other places we distribute video. And we're very interested in your comments. We are doing an early Rust implementation of this on top of our existing Rust stack. But there's currently no formal specification and there's no test vectors yet. So again, this is what area where we hope that we'll get some early community feedback to help us understand your needs and how to steer our direction with this. So what does a XID actually look like? What am I talking about? So a XID is a 32-byte unique identifier. We've talked about CBOR before. That's the concise binary object representation. That's like a binary form of JSON, if you're familiar with that. And this is just a string of numbers that has a CBOR tag, the XID would tag, which is also a number. It all comes down to bits at the lowest level. But this is how it's represented visually, XID, and then this long string of hexadecimal digits. The CBOR structure itself adds only 5 bytes. So you can see here where I've translated that into the actual number, 40,024. That's the number assigned to XIDs. And you see the actual bytes output for this. And you can see there's 5 bytes at the beginning before that, the number that begins 71274. And that's the tag. And it only adds 5 bytes of overhead. So to just pass a XID, it's 32 bytes plus 5 more, 37 bytes. But for visual use, we're often going to abbreviate that because XIDs are so unique. We only really need 4 bytes for most practical purposes to identify XIDs uniquely to users. So we often will write it this way. But and this can be considered a XID's kind of unique human readable name. So it's very unlikely that even 4 bytes are going to collide. It's astronomically unlikely that 32 bytes will ever possibly collide. And it's important that these bytes be random, and I'll explain in a moment how we ensure that they are random. But we want to make this name as recognizable as possible because this could stand in for a person, a company, any other kind of entity. So we want to make sure these entities are highly recognizable across the internet. So one way of doing that is we can translate those 4 bytes into what we call byte words. Byte words is something we've also developed at Blockchain Commons. It's a curated list of 256 4-letter English words. We had a number of very careful selection criteria we used in adopting this. We have a link here to our byte words paper, and we use byte words for a number of things in our stack. But again, this translates those numbers, which are kind of hard to remember and relay to 4 unambiguous 4-letter, easy to remember words. We're also doing some other experiments. For example, we're experiencing what we call Bytemoji, where we've selected 256 curated emoji, again, with very careful selection criteria for recognizability and distinction. And you can also translate those 4 bytes into these Bytemoji and have a very visual way of recognizing a XID at a glance. We can go even beyond that. We have another technique called life hash. Life hash is a beautiful and memorable visual image. Byte words and Bitmoji, as I mentioned, only use 4 bytes of the ZID, which is very unique. But life hash uses all 32 bytes, so it's extremely unique. And if even one tiny bit in that 32 bytes changes, the life hash changes entirely. So these techniques can all be combined. You can pair these up, and so people basically know what they're looking at belongs to me, belongs to you, belongs to Christopher, belongs to anybody. So how do you handle ZIDs? Well, a ZID can be converted to a URI. URLs are the most common form of URIs, but we have a format called the Uniform Resource, or UR, and this is a UR:ZID, which packages up that ZID in a form that's easy to copy and paste and move around. Now, a ZID itself is a pointer. It basically refers to something. If it's my ZID, it refers to me. If it's your ZID, it refers to you. But how do we access the deeper information that a ZID actually points to? So that gets us into the subject of resolving a ZID. Now, when you type a URL into your web browser, it resolves that using the DNS system to an actual server, which is an IP address, which is 4 numbers, and then it goes out and gets the data from that server. So there's a similar process with ZIDs. So a ZID by itself doesn't include a resolution method. You know, when you type a URL into a browser, you type HTTPS, that's the resolution method. It's basically do hypertext transfer protocol secure, and it's going to use DNS and all these things. Well, ZIDs are just this number and just this tag. You saw the exact binaries. There's no resolution method built into a ZID. But if there's a universal resolver, and we hope to specify a universal resolver with open source servers anybody can run, similar to the DNS system, then this is actually all you need. But some people who use ZIDs need actually other ways to resolve ZIDs. So if we need custom methods, we actually can compose a little Gordian envelope. And if you're familiar with the Gordian envelope, it's a subject, which in this case is the ZID, and the number of assertions about that subject, predicate object pairs that tell you something additional about that subject. So we can compose a little Gordian envelope and add these dereference via, which you see there's URLs there. There's a Bitcoin transaction that could refer to a transaction on the blockchain where that actually can help you direct you to more information. But you can have any number of different resolution methods that can be packaged up with the ZID in a Gordian envelope. So, and resolving these returns a ZID document. We'll talk a little bit more about what a ZID document is in a moment. In fact, a ZID with a resolution message is a tiny ZID document. So you're actually looking at a ZID document right here in kind of very minimal form. So this envelope, just like I showed you, the ZID can be a UR. Well, this envelope itself can be packaged into a ZID UR as well. It's longer because it has more information in it, but looks and acts just like the same as a bare ZID. And so you pass it around just like the bare ZID, but it has more information inside it. So any UR ZID can be completely self-describing. So how do you actually create a ZID? So first you generate a key pair. You're probably familiar with public key cryptography, or where you have a public and private key pair. And this can be any kind of key. Some of the more popular ones are ED25519, BIP340 Schnorr, or ECDSA, things like that. We recommend BIP340 because it's very easy to use it with multi-signature protocols like MuSig2 and Frost. And we call this key, in particular, that you're using to generate the ZID, the Genesis key, and you'll understand why it's distinct in a minute. So you encode that Genesis key to CBOR, and because CBOR includes both the type of key as well as the key itself, then the CBOR encoding is unique to both the key and the type. And then you take the SHA-256 digest of that CBOR. So this is basically a cryptographic digest algorithm that gives you 256 apparently random bytes, but they're not at all. One input gives exactly one output. And that's your ZID. That's exactly how you arrive. In fact, this number you see on the screen here, I actually used our Rust code to actually generate this ZID based on this process. So because you generated this ZID using a private public key pair, you can show part of that, the public key in particular, and prove certain things about it. First of all, you can prove global uniqueness because you generated that private key. It's unique to you and you keep it secret. You're actually proving that the ZID is globally unique. And you're also proving randomness because the SHA-256 is based on the public key, and SHA-256 always, no matter what you put into it, outputs an even distribution of what appear to be random bytes, but are in fact absolutely tied to what you put in. So you're proving these two things. So XIDs are guaranteed to be uniformly random sequences of numbers. Not truly random, they're pseudo-random in the sense that they're dependent on their input. But now I'm talking about these proofs. You're saying, okay, I can prove this is random. I can prove it's globally unique. Well, how do I prove that? Well, that's where we get back to the idea of a XID document. So a XID document is a Gordian envelope that packages together several things. It's the XID itself, and you see that there at the top. And the Genesis key, you see key, public signing key, and a signature made by the Genesis key. And you see that verified by a signature. The envelope itself with the XID and those two assertions in it is then wrapped, and then that wrapped envelope is now signed. And this is the interesting thing, because in a lot of systems, when you create an identifier like this using a key, you can never change the key. You're stuck with it, and you're stuck maintaining the private half of that key. And if it ever gets compromised, your entire identifier is compromised. And we wanted to find a way around that. And we think we've done that, because the Genesis key in a XID can actually be rotated without invalidating the XID. And I'll talk about how to do that. So your XID can be good forever, basically, even if you have to rotate the keys. So as I mentioned, this is a small XID document, but what other kinds of things can a XID document actually hold? So one thing it can hold is resolution methods. We've already talked about this before. So when you hand somebody a XID document, they can, that may have certain parts of it either elided, that's removed by you, or just not present, then they can actually go resolve it and not just find this XID document, but actually the entire history of revisions of the XID document. And that's actually super important. So this affords the discovery of the most recent revisions of the document, but as I mentioned, the whole history. And a universal resolver method, because I mentioned that before, could also resolve bare DIDs with no resolution methods. So notice now the key has changed from a public signing key to a public key base. So you can include keys for signing and encryption. So signing basically gives you security to know that whoever sent you the message is the person who signed it. Encryption gives you the idea, gives you the confidence that the message has not been intercepted by anybody because it's addressed just to you. So keys for signing and encryption. You can add individual keys, as you saw with public signing key, or you can use a public key base, which packages both a signing public key for signature verification and an agreement public key for encryption together, because together they give you everything you need to communicate securely and privately. So you can also, in a XID document, you can have permission delegation. So in this case, you see there's a controller assertion, and there's also the allow all assertion. So XID documents use what's called a deny first permission structure. If you don't say you granted certain permissions, everything is denied. You can't do anything with it. And it's the resolver network that prevents you from doing something with it. If you submit something to resolver network or revision the document, and you're not doing it according to the permissions in the document you're revising, the resolver network will just drop it on the floor. It'll ignore it. So in this example, though, all permissions, which were originally part of the assigned to the Genesis key, have now been delegated away from the Genesis key. Well, how do I know? Well, a different controller XID has been assigned, and that controller, as well as the allow all, applies to the other things at its level in this XID document, which includes the key and that permissions. So this controller, and notice that I've notated here that the key here is no longer the Genesis key, but the XID itself is still good. So if I revise the document using the Genesis key, but using this, then the Genesis key is now good for nothing but showing that at the beginning, that key was used to create the XID. So resolvers and the verifiable history of a XID prove that XID is still valid. So you can also have keys with fine-grained permissions. Here you see you have a key group. The key group has its own controller. That controller has its own dereference via its own resolution method. It defines one or more keys. In this case, that key itself is denied certain permissions, like the verify permission, which you need to actually revise the XID document. So we're including the resolution methods and other endpoints. For example, that key is used for messaging, messaging.example.com, but not verification of the envelope itself. And another thing that you can add are what's called provenance marks. Provenance is the origin or history or pedigree of something. And a provenance mark is a way of establishing a distributed traceable hash chain of revisions. You can go to provemark.com or that URL to find out more about it. It's also open source. And it's basically a way that you can mark any digital document as having a lineage going back to the start, and you don't need a blockchain or anything like that to do it. It's like your own personal blockchain. And that basically gives you a way, when you receive a ZID document, of actually tracing back its history in a verifiable way. So one of the superpowers of Gordian envelopes is elision, which is basically removing data, and the holder of a document can do that before sending it on to somebody else. So ZID documents, like you just saw, can be vended with all their information intact, or you can elide it for a specific purpose by the vendor. In this case, we've removed certain things that aren't necessary for a certain kind of transaction. And that idea is minimal disclosure, the idea that you only reveal what you need to actually perform a function. And this is basically a privacy preserving strategy. And the important thing with Gordian envelope is that signature still verifies, because when you elide things using Gordian envelope, signature itself, if there's one on the outside, still verifies, because all the hash tree, the digest tree of the envelope is still intact. In fact, you can elide most of the assertions in the document and simply at first reveal that you have a signed ZID and that the enclosed key verifies it. And that's it. So you can basically use progressive trust to reveal more and more about the ZID document as you trust the other parties. So what are the uses of ZIDs? Well, they're a new form of decentralized identifier. As I demonstrated, they go beyond the capabilities of W3C DID controller documents. Elision determines who gets which keys, endpoints, assertions, endorsements, and other sensitive details. And we didn't go into it, but endorsements could be various things like credentials or documentation of accomplishments, things like that. You can create many new types of secure credentials and entitlements tied to a particular identity that could represent, again, anything. It could be anything from yourself to a university, to a business, to a light bulb in your Internet of Things. Some of you might be familiar with the Nostr social media, distributed social media protocol. One of the things that you can't do with Nostr is rotate the keys. So you generate a public-private key pair, and that becomes your identity, but there's no way to actually change the, if you lose the private key or it's compromised, then your identity is basically compromised. Whereas we're providing a methodology here where you can rotate your keys and keep your identifier throughout its lifetime. And of course, you can also use record the provenance of digital assets without a blockchain using a ZID with provenance marks. So that's my presentation. Definitely open to questions. Christopher or I are always available to answer the community's questions. We're really looking forward to engaging with you on this exciting new topic.